Hello, today we're going to be taking a look at second order linear ordinary differential equation with constant coefficients. And we're not given any values, we're just going to solve this in general. So it's going to be kind of like a brief primer. And hopefully it serves as a really good introduction to those just starting the topic as well. The problem statement gives us the second order differential equation mx double prime plus gamma x prime plus kx equals a naught times sine of omega t. This is called a forcing function. And that will come into play later when we are evaluating the particular solution to this differential equation. We know that the form of the differential equation at the end of this entire process is going to look like this. This is the sum of the homogeneous part of the solution and the particular part of the solution. To get this equation into a standard form, I want to divide by m because I want to make the leading coefficient equal to 1. I'm also going to define a couple of dummy variables. And I will recast this equation with these dummy variables substituted. For the homogeneous case, the forcing function is set to be equal to 0, and I will write a characteristic equation for this part of the solution. I can do this by letting x equal to the exponential function of r times t. Taking successive derivatives and then substituting them back in to this differential equation will give me my characteristic equation. I will immediately factor out the exponential function when I do this. And we are left in the parentheses a polynomial in R with coefficients 1, 2 beta, and omega naught squared equal to 0. We know that the exponential function can never be 0. That must mean that the polynomial in this equation is the thing that is equal to 0. And we are given in the problem statement as well that we are dealing with the underdamped case. Where beta is less than omega naught. And this relationship basically comes from the idea that the damped frequency is equal to the difference of squares between these two, and we end up getting a real number, which is what tells us that we are underdamped. From here, we can just begin solving for the particular solution. This is done by guessing, and it sounds very not precise. However, it actually has a lot of intuition behind it, because if you take successive derivatives of sine or cosine, you end up just like in this kind of circle, right? It ends up repeating after you take the fourth derivative. And so it would be clever then to guess that the functions x in this equation are some linear combination of sines and cosines, since the equation just involves taking successive derivatives and you have a forcing function that has a sine term in it. It is wise to choose this linear combination of trigonometric terms for your particular solution. So I'm just going to do that right now. And remember, I said linear combinations, so that involves coefficients as well, and I'm just going to call those D and F. The dampened frequency, and this can often be written as just one function using trig identities. And so here we have our particular solution. We said at the beginning that the form of the solution to this diffie-q is just going to be the sum of the homogeneous part and the particular part of the solution, and which I'll just sub in right here, right now. And that is the solution that solves the differential equation that models this underdamped oscillatory motion. A couple things to note, and this just kind of comes from the realm of Euclid in Pythagoras, right? So when you do this trig stuff right here, this combination, there's some undefined variables here, and I'm just going to put them down real quick. And so, with this information, I hope this was a good primer and review for those revisiting the topic. And I also hope that it was easy to follow for anybody starting their study in differential equations. It truly is a fascinating subject, and I would love to do more. This is a very basic example, and I do plan on sharpening my skills a little more, so I'll make videos about that. But if you enjoyed this video, please like and subscribe, as there will be more similar to it as I finish my degree in engineering. Um, and also leave me a comment and let me know if there's anything that you would like me to cover that is relevant to this type of material. With that said, thank you for viewing and have a wonderful day.